The mole and Avogadro's number. The mole is an amount unit similar to familiar units like pair, dozen, gross, etc. So we know that a pair is talking about 2, a dozen is talking about 12. So if I say a dozen eggs, we know we're talking about 12 eggs. If I say a dozen chickens, we're talking about 12 chickens. The mole is a set quantity. The mole is defined as the amount of a substance containing the same number of discrete entities, such as atoms, molecules, or ions, as the number of atoms in a sample of pure carbon-12 weighing exactly 12 grams. So this is how we derived the mole. This is how we're saying what the mole is and where it came from. But functionally, the mole provides a link between the mass of a sample and the number of atoms, molecules, or ions within that sample. The number of entities composing a mole has been determined to be 6.022141179 times 10 to the 23rd. This constant is named after the Italian scientists Amedeo Avogadro, also known as Avogadro's number. So Avogadro's number, and this is a very important number that you should just internalize, memorize, and know for this course, is 6.022 times 10 to the 23rd. So if I were to say I have a dozen eggs, we know that we have 12 eggs. But if I say that I have Avogadro's number worth of eggs, we're talking about 6.022 times 10 to the 23rd eggs. That's a ton of eggs. Another way to say that, though, is if I have a dozen eggs, I have 12 eggs. Or if I have a mole of eggs, I have 6.022 times 10 to the 23rd eggs. A mole is the number of entities equivalent to 6.022 times 10 to the 23rd. So the masses of one mole of different elements are different, though, because masses of individual atoms are drastically different. So if I want to compare a dozen eggs to a dozen chickens, obviously the dozen chickens are going to have a greater mass. Similarly, if I want to compare a mole of carbon to a mole of nitrogen, they're going to have different masses. Now, how do we determine the mass? How do we know what mass this is? So if we pull up a periodic table, and this is the exact periodic table that's on the last sheet of that chemistry aid sheet, we can see the masses are listed right in the periodic table. So let's just look at boron, for example. Boron is capital B. B is the element symbol for boron. And then we're given two numbers here, and we've already discussed what these two numbers are. The atomic number is equivalent to the number of protons in the nucleus, and in an uncharged atom of boron, this is also the number of electrons that are found in the nucleus. Now the atomic mass, or mass number, is 10.811. So 10.811 is where we get the mass from. So not only is this equivalent once we round it to the number of protons and neutrons in the nucleus of an atom, this is also equivalent to what the mass of one mole of this element would be. So if we take 1 mole of boron atoms, and 1 mole, we're talking about 6.022 times 10 to the 23rd atoms of boron, it would have a mass of 10.811 grams. So the mass comes directly from the periodic table. Here you can see a picture of the mass of different elements. You can see physically that the quantities look different, and then you can also look at the mass and how those are different. But in each one of these samples, each one of these is 1 mole. It's 6.022 times 10 to the 23rd atoms of that element. This can be used as a conversion factor. So similar to how we've done unit conversions before, we can use this as a conversion factor. The problem here is telling us to convert 3.5 moles of helium to the number of helium atoms. So we're starting with moles, and we're converting to the number of atoms. Our conversion factor is 1 mole of anything, any element, is 6.022 times 10 to the 23rd atoms of that same element. So we start with what we are given in the problem, 3.5 moles. And we're going to treat this just like any old unit conversion. Mole is on the top, so we're going to put mole on the bottom. And we want to convert 2 atoms. We're going to put atoms on the top here. 1 mole is equal to Avogadro's number of atoms, 6.022 times 10 to the 23rd. So when we do the math, we're going to multiply across the top and divide away the bottom. Now, something that I recommend when putting Avogadro's number in your calculator, anytime you do an equation that's going to include a number that's in scientific notation, you always want to put that entire number in parentheses. So you're going to actually type in your calculator 3.5 times, and then do your parentheses, 6.022 times 10, and then you can do your caret key and 23, and close your parentheses. Then you can do equals, and that will give you your answer. If you don't put this in parentheses, it's not going to follow the appropriate order of operations. Remember, from algebra class or from a math class, order of operations, you're going to want to do things with exponents. Within the parentheses, you want to start with the exponents, and then you go to the multiplication, and then you do the things outside of the parentheses. So then multiplication, and then last would be addition or subtraction. So I'm going to go ahead and type this into my calculator. So 3.5 times parentheses 6.022 times 10 to the 23rd equals, and I made sure I closed my parentheses before pressing equals. So this is going to be 2.1, and I'm going to round to 3 sig figs, because remember, in this class we want to make sure that we are consistent with our rounding. 2.11 times 10 to the 24. And we have to put a unit on this. So moles crosses off, and we end up with atoms. Okay, now we're converting atoms to moles. So convert 1.1 times 10 to the 22 silver atoms to moles of silver. So we're starting with atoms, we're converting to moles. So 1.1 times 10 to the 22nd atoms, parentheses, we have atoms on the top, we're going to put atoms on the bottom. We're converting to moles. And moles, M-O-L-E, is abbreviated M-O-L. Now, what's our conversion factor here? Well, 1 mole is equal to Avogadro's number of atoms, 6.022 times 10 to the 23rd equals. So we're going to multiply across the top and divide away the bottom. Remember, anytime you put a number that's in scientific notation in your calculator, you want to make sure to have parentheses around it. So when I type this in my calculator, I'm going to go parentheses 1.1 times 10, and I'm going to do the caret key to do the exponent, 22. And then I'm going to multiply that, and remember, close your parentheses, multiply that by new parentheses, or sorry, we're dividing. Let me get rid of this. We're dividing. Divided by 6.022 times 10 to the 23rd. Caret key for the exponent, and then I can press equals. If you're curious what calculator I'm using, I have had this calculator since 2004, and it has served me well all of these years. Never had to buy a new calculator. It is a TI, Texas Instrument, 30X 2S. Any calculator is probably going to be fine. This is the calculator I use, and it has everything that I need for all of my science classes. So I strongly recommend this one, or if you can find something similar to this one, it will work. So we're going to go ahead and type this in our calculator now. So parentheses 1.1 times 10 caret key 22, close my parentheses, divided by new parentheses 6.022 times 10 caret key 23, close my parentheses, equals 0.0183. Again, I'm going to round to 3 sig figs. And what is my unit? So we crossed off atoms. We are left with mole. Mole. And that's what the problem was asking for. Moles of silver. And just to remind you, that is talking about my calculator. Okay, so I'd like you to go ahead and pause the video, try to figure this one out on your own, and then we'll unpause the video and go through this one. All right, so moles, we're going to atoms. 2.4 moles of any substance can be converted to atoms using the conversion factor of Avogadro's number. So if we have moles on the top, we're going to put moles on the bottom, and we're converting to atoms. 1 mole is equal to Avogadro's number of atoms, 6.022 times 10 to the 23rd. When I type this in my calculator, remember to put parentheses around Avogadro's number, but we're going to do 2.4 times 6. Close a parenthesis, new set of parentheses, 6.022 times 10 caret key 23, close the parentheses, equals 1.45 times 10 to the 24th atoms. So I'm going to give you a minute to work on this one. You can pause the video and then resume when you're ready for the answer. Okay. How many moles of HCl are present in 4.3 times 10 to the 23rd molecules? So we have this. We're converting to moles. 4.3 times 10 to the 23rd molecules. And molecules can be treated in the same way as atoms. So we put molecules on the bottom, and we're going to put mole on the top. And our unit conversion is 1 mole is equal to Avogadro's number of atoms, molecules, chicken, ducks, eggs, whatever it is. 1 mole we know is 6.022 times 10 to the 23rd. And we're going to do the calculation, and we end up with 0.71 moles. So you would, again, put parentheses around this when you're typing this in. You're going to multiply across the top, divide away the bottom. So when you do the division, you're going to put parentheses around this number before you press equals. So, looking at nails, so 1 dozen large nails and 1 dozen small nails are going to have different masses. They're not going to weigh the same. Just like different elements are going to have different masses. And I talked about this before, like a dozen eggs is going to have a different mass than a dozen chickens. So the molar mass of any element, the mass of 1 mole of atoms of that element, is equal to the atomic mass of that element expressed in atomic mass units. So 1 copper atom has an atomic mass of 63.55 AMU. Where does that number come from? We go back to the periodic table. We find copper on here, and Cu is right here, 63.546, which can be rounded to 55. So 63.55, right on the periodic table. 1 mole of copper atom has a mass of 63.55 grams. The molar mass of copper is thus 63.55 grams per 1 mole. The mass of 1 mole of atoms changes for different elements. So you can see on the periodic table, all of the different masses are different. The lighter the atom, the less mass in 1 mole of that atom. So now we're going to try to convert between grams and moles. So 0.58 grams of carbon, how many moles are in that? So calculate the number of moles in 0.58 grams. So we're going to start with 0.58 grams, and we're actually going to write down the element symbol so we know what element we're talking about. Now before, when we were talking about atoms or molecules using Avogadro's number, the element didn't matter too much because no matter what, it's the same number of particles within a mole. But because we're talking about mass, mass does matter depending on what element we're talking about because atoms have different masses. So we're actually going to write this, and just to be safe, we can always write the symbol in all of our calculations just so we can keep track of it appropriately. So we're going to have grams on the top, and we're going to do a unit conversion to moles. So grams is on the top, we're going to put grams on the bottom, and then we're going to moles. Moles. So how do we figure out this conversion factor? Well, 1 mole is equivalent to the mass that we find on the periodic table. So we're going to have to go back to our periodic table. And we go to carbon, and we see that the mass of carbon is 12.011. So 0.58 grams of carbon, grams to moles, 1 mole is equal to 12.011 grams of carbon. And we're going to multiply across the top, divide away the bottom. So that becomes 0.58 divided by 12.011, which is equal to 0.0483 to 3 sig figs moles of carbon. I'm going to let you pause the video and work through this one. And then when you're ready, unpause and I'll go through the answer. Okay, so we have 2.4 moles of carbon and we're trying to get to grams of carbon. So we go 2.4 moles carbon, put moles of carbon on the bottom, grams of carbon on the top. 1 mole is equivalent to 12.011 grams, and you can get that off the periodic table. So 2.4 times 12.011 equals 28.8 grams of carbon, because the moles cross out and you're left with grams, and that's what we wanted in the problem. And this shows you a step-by-step problem written out for how to convert from grams to moles to atoms. So sometimes you're given a mass and it's asking for, well, how many atoms are in it? Moles is a required intermediary step. So there's no direct conversion between atoms and grams. We always want to get to the mole first as a step in between. So if we want to convert from 0.58 grams of carbon to atoms of carbon, first we're going to convert to moles, and then from moles we're going to convert to atoms. So, how many aluminum atoms are in an aluminum can with a mass of 16.2 grams? So if we have 16.2 grams of aluminum, and we want to get all the way to atoms, we're actually going to need 2 sets of parentheses. First, we're going to take grams to moles. And that should be a lowercase l. And then from moles of aluminum, we can get to atoms of aluminum. Anytime something's on the top, you're going to want to put that unit on the bottom of the next parentheses, because then it'll cross out. So we put moles on the top, moles has to go on the bottom, and then we end up with atoms up here. Now we have to fill in our conversion factors. Well, 1 mole is equivalent to 26.98 grams of aluminum. Where did this number come from? The mass on the periodic table of elements. Over here, we have the conversion factor of 1 mole is equal to Avogadro's number worth of atoms, 6.022 times 10 to the 23rd. We do not want to round in between steps. So what we're going to do is we're going to multiply the entire top and divide it by the entire bottom. So it's 16.2 times 1 times 6.022 times 10 to the 23rd divided by 26.98 times 1. So we don't have to multiply by the ones because we know that that's not going to change the value of the number. So in our calculator, we can put 16.2 times 6.022 times 10 to the 23rd. Remember to put this number in parentheses. And then go ahead and press equals. You want to keep that full number on your calculator and then divide by 26.98. So I'm going to go ahead and do this in my calculator. 16.2 times parentheses 6.022 times 10 caret 23, close the parentheses, equals. With that number on my calculator, I'm just going to click divided by, and now it's showing me the answer is going to be divided by 26.98. And that becomes 3.62 times 10 to the 23rd. And our unit is atoms, because grams crosses out, moles crosses out. We're left with atoms, and it was asking for atoms in the problem. So now, if you have a 16.2 gram can, aluminum can, you know how many atoms are in that aluminum can. Probably don't care too much, but it's really cool if you think about it. All right, so go ahead, pause the video, work through this one. Okay, so when we look at this one, we're starting with atoms and we're converting to grams. But we have to have that intermediary step of moles. So we have to go to moles before we can go back to grams. So we have 3.01 times 10 to the 23rd atoms, and lead is Pb. That's our element symbol for lead. So atoms is on the top, we put atoms on the bottom. We have to get to that intermediary step of moles. And our conversion factor here is 1 mole is equal to Avogadro's number of atoms, 6.022 times 10 to the 23rd. You know, the number of times that I'm saying this in this video, you will probably never forget Avogadro's number. And this isn't the only lecture we're going to use Avogadro's number. There's many other times throughout the course that we will be using this. So by the end, you're just going to have this memorized. So now from moles, we want to get to grams because they're asking for mass. So since moles is on the top, we're going to put moles on the bottom, and we're going to grams. What's our conversion factor here? Well, 1 mole is equal to the mass from the periodic table, 207.2 grams. To get our answer here, we multiply across the top, divide away the bottom, and our answer is 104 grams. All right, so molar mass of compounds. So far, we've just been talking about the mass of individual elements. So we had the mass of lead. In this problem, we were talking about the mass of aluminum. This one, we were talking about the mass of carbon. But what if we have a molecule? The mass of a molecule or a compound can be calculated by calculating the mass of each one of the individual atoms within that compound. So here we can see in CO2 we have 1 carbon and 2 oxygen. So for 1 carbon has the mass of 12.01. So 1 mole of carbon has 12.01 grams. Oxygen, the mass of 1 mole of oxygen is 16 grams, but we actually have 2 of those, so we have to account for those 2. So we have 1 carbon with that mass, 2 oxygen with that mass, and we just add them together. Now this is our molar mass of carbon dioxide. So I'm going to go through the first one, and then I'm going to let you guys work on the next 2. Calculate the molar mass of each of the following compounds. So we have 1 hydrogen and 1 chlorine. So this one should be relatively easy. So we have the hydrogen, the chlorine, and then we're going to add those together. Where do we get these masses from? We're going to go to our periodic table of the elements. We're going to go up to hydrogen. Hydrogen is 1.008, and chlorine is 35.453. So I'm going to round these just for the sake of this problem because these are on 2 separate screens. So hydrogen we're going to round to 1, chlorine we're going to round to 35.5 grams. So hydrogen 1 gram. Chlorine, 35.5 grams. And since there's only one of each, we don't have to do any multiplication. We're just going to add them together. And we get 36.5 grams. For the next one, you want to make sure to figure out the mass of aluminum, carbon, and oxygen, and multiply it by the number present in this whole compound. And then for the last one, you're going to want to do nitrogen, hydrogen, phosphorus, and oxygen. Again, you want to figure out how many of each to do the multiplication. So go ahead and pause the video and work through these, and then I'll come back and give you the answers. All right, so if we look at this one, aluminum. How many aluminum are there? There's 2. And what's the mass of aluminum? We got to go to our periodic table. And aluminum is 26.98 grams. Here, we're looking at carbon. Now, since this 3 is on the outside of the parentheses, we have to carry it in. So that actually makes that 3 carbon. So there's 3, and I know that carbon is 12.01 grams. For oxygen, so this 3 gets carried in. We don't add them, we multiply them. So 3 times 3 is 9. And oxygen, I know, has a mass of 16 grams. Now, I'm going to add those all together. And I can do this in my calculator. So I can do 2 times 26.98. And you want to do parentheses around each one of these. So parentheses, 2 times 26.98, close the parentheses, plus parentheses, 3 times 12.01, close the parentheses, plus parentheses, 9 times 16, close the parentheses, equals 233.99, in other words, 244 grams, rounded to 3 sig figs. And we go through the next one. We have nitrogen, hydrogen, phosphorus, and oxygen. Now, this 3 gets carried in, so there's actually 3 nitrogen. The mass of nitrogen is about 14. Let me just take a look. Yep, we're going to call it 14. Hydrogen, we have 3 times 4 of hydrogen, so we have 12 hydrogen, and each one of those is 1 gram. Now, we have 1 phosphorus. The mass of phosphorus from the periodic table is up here, 30.974. Let me go back there. Did I do that right? Yeah, 30.974. And oxygen. So we have 4 oxygen, and oxygen is 16. We're going to add these all together, and we can do it all at once in our calculator. Parentheses, 3 times 14, close your parentheses, plus parentheses, 12 times 1, close your parentheses, plus parentheses, 1 times 30.974, close your parentheses, plus parentheses, 4 times 16, close your parentheses, equals 148.97, in other words, 149 grams rounded to 3 sig figs. Okay, so now converting between grams and moles of a compound. So the mass in grams of calculate the mass in grams of 1.75 moles of water. So we have 1.75 moles, we're going to question mark grams, 1.75 moles of H2O, moles H2O, grams of H2O. 1 mole is equal to the calculated mass from the periodic table. So H2O means that there's 2 hydrogen, and each hydrogen is 1 gram. And O, there's 1 oxygen, and each oxygen is 16 grams. So when we add this up, we're going to get 18 grams. So 18 grams. And all we do is multiply across the top, divide away the bottom, equals 31.5 grams. So now we're going to take it even farther and go between molecules and mass. Remember, we have to have that intermediary step of moles. So we're going to go from 4.78 times 10 to the 24th molecules to moles, and then moles to grams. Go ahead and pause the video, work through this problem, and then we will unpause and go through the answer. Okay. 4.78 times 10 to the 24 molecules of NO2 molecules is on the top, we're going to put molecules on the bottom, and we got to go to moles first. Since moles is on the top, we're going to put moles on the bottom, and we want to end up with grams. What's our conversion factor here? Well, 1 mole of anything is equal to 6.022 times 10 to the 23rd molecules of anything. And what's our conversion factor here? Well, if we want to look at mass, 1 mole is equal to the calculated mass from the periodic table. So now we got to calculate what that mass is. N, there's 1 N, and nitrogen is 14 grams. Oxygen, there's 2 oxygen in NO2. So we're going to do 2 times 16, and we're going to add these up. So that's 1 times 14 plus 2 times 16. And we get 46 grams. 46 grams. So we're going to multiply across the top, divide away the bottom. .78 times 10 to the 24, close the parentheses, times 46 equals. Now we're going to divide that answer by parentheses, 6.022 times 10 to the 23rd, close the parentheses. We get 365. Molecules crossed off, moles crossed off, we're left with grams. So here's a problem that is solved out for you, and this is the one that I just did here. You can see that they ended up getting the same answer. You can go through the steps here and kind of follow along with what we just did. And here's just a couple more examples. Let's see. We did one from moles. Here we go. We'll do it in this direction, and this will be the last example that we go through. So go ahead and try to solve this. You can pause the video, and then I will go through how we would solve this, and then we'll move on to mass percent. Okay, so here you can see we have 35 grams, and they want us to go to molecules. So we start with 35 grams of H2O. We have to use moles as that intermediary, and they want us to end up in molecules. So since we have grams on the top, we put grams on the bottom. Grams can be converted to moles, and then moles can be converted to molecules. So in this problem, 1 mole is equal to the calculated mass from the periodic table. H2O we calculated previously to be 18 grams. Now here, our conversion factor is 1 mole is equal to Avogadro's number of molecules, 6.022 times 10 to the 23rd. We're going to multiply across the top, divide away the bottom. So in our calculator, 35 times parentheses 6.022 times 10 caret 23 equals, and then we're going to divide away 18 grams. That's going to give us 1.17 times 10 to the 24th. And we cross off our units, grams, grams, moles, moles. We're ending with molecules. Okay, so you guys can work through this problem, pause the video, and when you unpause, the answer is 2.53 times 10 to the 24th molecules. Here's another one that you guys can pause and work through. And when you unpause, it's 0.810 moles. One more example. You can pause the video and work through. And the answer is 6.39 grams. Okay, so mass percent or percent composition. The mass percent of an element is equal to the mass of that element in a sample of a compound divided by the mass of the whole compound times 100%. So percent composition is a list of the mass percent of each element in a compound. So Na2CO3 or sodium carbonate is actually 43.38% sodium, 11.33% carbon, and 45.29% oxygen. So how do we calculate the mass percent? First, determine the molar mass of Na2CO3. So we have 2 sodium, and the mass of each sodium is going to be 22.99. Then we have 1 carbon, and the mass of carbon is 12.01. Then we have 3 oxygen, so that's 16 times 3 grams of oxygen. When we add those together, we get 105.99 grams per mole. So that's our total. Then you're going to find the ratio of the mass of each element to the mass of the compound. So we can do the mass of sodium divided by the mass of the total compound times 100%. The mass of carbon in that divided by the mass of the whole compound divided by, or times 100%. And the mass of oxygen divided by the mass of the whole compound times 100%. So given C2Cl4F2, what is the mass percent of chlorine? So first we have to figure out the mass of the whole compound. So in this compound we have carbon, chlorine, and fluorine. We have 2 carbons, and each carbon is a mass of 12.01. We have 4 chlorines, and each chlorine is a mass of 35.5 grams. And these are coming directly from the periodic table. Then we have 2 fluorines, and fluorine has a mass of, I need to actually look that one up, I don't have fluorine memorized. Fluorine, we'll round that to 19. Grams. So 2 times 12.01 is 24.02. 4 times 35.5 is 142. And 2 times 19 is 38. And when we add those all together, 38 plus 142 plus 24.02, we get 204 grams, rounded to 3 sig figs. So if we want to get the mass percent of chlorine in here, we're going to take the total mass of chlorine, which is 142, divided by the mass of the whole compound, which is 204, and we're going to multiply that by 100%. So 142 divided by 204, 69.6%. So the mass percent of chlorine in C2Cl4F2 is 69.6%. So I'd like you to pause the video, work through each one of these, and determine the percentage composition of each of the compounds. All right, so hopefully you had an opportunity to work through those. I am going to go through the answers with you. So the first one, potassium. So there's 1 potassium, and potassium has a mass of 39 grams. There's 1 manganese, and manganese has the mass of 54.9 grams. There's 4 oxygen, and oxygen has a mass of 16 grams, so 16 times 4 is 64. So in total, if we add this up, 64 plus 54.9 plus 39, 157.9. Now, if we want to get the mass percent of each one of these, we would just divide the total mass of that part divided by the total of the whole compound. So 39 divided by 157.9 times 100% gives us 24.7%. And if we want to do this one, 54.9 divided by 157.9, we've got 34.8%. And for this one, we would do 64 divided by 157.9 times 100%. 40.5%. So that's the mass percent of each one of these. Nitrogen. So nitrogen has a mass of 14, but there's actually 3 nitrogen. So 14 times 3 is 42. Hydrogen has a mass of 1, but if we multiply this through, we actually have 12 hydrogens, so that has a mass of 12. Phosphorus has a mass of 30.97, so I'm just going to round that to 31. And oxygen has a mass of 16, but there's 4 oxygen. So 16 times 4 is 64. If we add these all together, 42 plus 12 plus 31 plus 64 is 149. To get the mass percent, you just divide each one of these by the total and multiply by 100%. So 42 divided by 149 times 100% is equal to 28.2%. 12 divided by 149 is times 100% is 8%. 31 divided by 149 times 100% is 20.8%. And 64 divided by 149 is 42.95, so 43%. HCl. So there's 1 hydrogen. Hydrogen is 1, mass of 1. There's 1 chlorine, and chlorine has a mass of 35.5. So 35.5 plus 1 is 36.5 total. So 1 divided by 36.5 gives us a mass percent of 2.7%. So then 97.3%. And our last problem here, we have aluminum. So aluminum, there's 2 aluminums. Each aluminum has a mass from the periodic table of 26.98 times 2 is 53.96. And we can round that to 54. Sulfur, there's 3 sulfur because we carry in this 3. Sulfur has a mass of 32 grams per mole. 32 times 3 is 96. And oxygen, we have to carry in the 3, so that's actually 12 oxygen times 16 grams per oxygen is 192 grams. And when we add that up, we get 342 grams total. So the mass percent, 54 divided by 342 times 100% gives us 15.8%. 96 divided by 342 gives us 28.1%. And 192 divided by 342 gives us 56.1%. So that's the mass percent of each one of those. So what percent carbon in here? You can go ahead and pause the video, work through the math on that one. When you unpause, 39.99%. And that is it for this lesson.